Welcome back to Chemisode, and this is the second part on our equilibrium series, where we're looking at equilibrium calculations. You are going to be introduced to two terms this time. We're going to look at the reaction quotient and the equilibrium constant, and this is obviously, we're going to be doing some calculations about these two things. First of all, let's define what these two things actually are. In equilibrium, well, for every reaction, we have a relationship between the amounts of products and the amounts of reactions. Okay, this relationship is known as a reaction quotient, and it involves the mole ratio of the reactants and the products and their concentration. This reaction quotient is given the term Q, and it is calculated by looking at the concentration to the power of the coefficients in a chemical reaction. And that's of the products divided by the reactants. So in this example here, we've got W plus X goes to Y plus Z, and we've got A, B, C, D for their what's it called, coefficients. Now we get products over reactants, so we get concentration of Y to the power of C, concentration of Z to the power of D, divided by concentration of W to the power of A, concentration of X to the power of B. So obviously it's products over reactants, concentration to the power of coefficients. So we put the coefficient to the power. Now this is known as Q. This is a reaction quotient. It can be calculated for any concentrations whatsoever. Now there's a special relationship, or there's a special term for Q when we reach equilibrium. When we have that concentration, which is at equilibrium, so when our concentrations remain constant, this is known as the equilibrium constant, and it's given the symbol K. So the fact of the matter is K is the value for Q at equilibrium. So when you have a system at equilibrium, Q is K. We'll get more into that a bit later on when we're doing actual calculations and thinking about what happens. But another important thing to say is K is temperature dependent. So K needs to have a temperature normally assigned to it. So that's because equilibrium is temperature dependent as well. So if you change the temperature, you change the concentrations at equilibrium. And again, more on that a little bit later on. Let's have a look at some examples here and look at two examples, and then we'll go into some more calculation of K or Q values. For this reaction here, if we want to write the K value, or the Q value I should say, the reaction quotient for this, the expression for the equilibrium constant, what we'll do is we'll go products divided by reactants, concentration to the power coefficient. So this guy becomes this, where the expression for K is concentration of carbon monoxide times the concentration of chlorine gas divided by the concentration of this bad boy here. This is the value for K. Our reaction over here obviously is a bit different. We've got hydrogen and iodine forming hydrogen iodide. Reaction quotient, or the equilibrium constant, the expression for this is obviously concentration to the power of coefficient. The coefficient here is 2, so that's for the power of 2, divided by concentration of these two multiplied together. We get K. Interesting fact about these two things, even though we're working out the equilibrium constant, or the reaction quotient for these two reactions, they have different units. So K, the units of K will change depending on what your ratios are like. To work them out, we just simply work out algebraically what the units will be. Obviously, concentration has the units of molar. So we have molar times molar divided by molar. Obviously, concentration times concentration divided by concentration means concentration squared, molar squared, divided by molar, which gives you the unit of just simply concentration, which is molar. So our unit here is molar. Over here, though, if we rewrite these as being our units, we get molar squared divided by molar times molar, which gives you molar squared divided by molar squared, which cancel out and give you a unit of 1, which is basically no units whatsoever. So obviously the units of K change depending on your reaction. And each time you calculate K or the reaction quotient Q, you need to think about what your units are going to be. And the simplest way of doing that is just to think about concentration as being capital M and then do it algebraically like I have here. So that's calculations, how to write the expression and how to work out the units there. All right, what we're going to do now, before I get into this, I might do a couple of examples and of calculating the equilibrium constant and various things about, I'll basically just do a few questions for you. So I'll get into those now. Okay, here's our first question for equilibrium, and it's using this equation here, where it's the formation of hydrogen iodide from hydrogen and iodine. The equilibrium constant is given to us here, Kc. Equilibrium constant is given to us as 50.3 at a certain temperature, being 731 degrees Kelvin, or just 731 Kelvin. And we have 0.1 molar of each gas is introduced into the container, or a container, at this temperature. Notice the same temperature means we can use K as being our equilibrium constant. Each gas means this one, hydrogen, iodine, and hydrogen iodide. Just make sure that's easy to see as a gas there as well. Question is, do we have an equilibrium? So is this system in equilibrium with 1 molar of each of these gases? And if not, which direction will the reaction proceed? Which one will be favoured? So to do this, we need to work out if 1 molar of each of these gases makes our equilibrium constant. So we're going to work out our reaction quotient is equal to our products, which is our hydrogen iodide, squared, divided by our concentration of our reactants, which are these two gases here underneath. This is going to be equal to, well, obviously our concentration of each gas is 0.1. So it's going to be 0.1 squared divided by 0.1 times 0.1. This is equal to 0.01 divided by 0.01, which equals 1. Okay, now notice, this is not equal to that. So we do not have equilibrium. There is no equilibrium when we have this way. Which way will be favoured? Well, we need to think about it. K is larger, K here is larger than our reaction quotient. So what has to happen is we have to end up with more products to reach equilibrium. So the reaction that's going to be favoured is the Ford reaction is favoured because we need to make more products. We need to increase our reaction quotient for it to get to our K value there. So that's simply working out if something is in equilibrium or not. It's writing the reaction quotient and calculating it for the given values that we have. Okay, here's a second question, and it's to do with equilibrium again. And it says a 1 litre container contains 1 molar of phosgene, which is a gas, which is this gas here. It decomposes according to the reaction here. So we have phosgene, obviously forming carbon monoxide and chlorine gas. It says at equilibrium, the concentration of chlorine gas is 0.028 molar. Okay, and we need to find out what the concentration of the other gases are, first of all, and then what the K value of the reaction is as well. So if we're not given a K value, or if we have a reaction which is happening and they say they give you some concentrations, chances are that you need to work out what the concentrations of things are at equilibrium. So to do that, what we need to do is draw up a little table. So on this side, we're going to have our concentration here initially, then we're going to have concentration change, and then we have concentration at equilibrium here. Across the top here, we're going to just put our different gases here. We have Cl2 and CO and Cl2 here and Cl2 here. Okay, so what we put in is our, first of all, our initial concentrations of the things that are given here. So it says at the start, we have a 1 litre container contains this 1 molar of phosgene. Okay, doesn't contain anything else. So initially, we have 1 molar of phosgene and 0 here. What it says, also is that at equilibrium, the concentration of chlorine gas is 0.028 molar. So therefore at equilibrium, chlorine is 0.028 molar. Okay, so what we can work out is our changes. Now our changes deal with the mole ratio. Okay, obviously chlorine has gone up, I'm going to put this in a blue colour, has gone up 0.028 molar. Okay, according to my reaction, that means that this one must have gone up by the same amount as this. So this one must have changed by the same amount as this, which means plus 0.028 molar. Okay, because we have a 1-to-1 ratio here. Obviously, different ratio means you get different amounts going up and down, but you get the idea. And that means that this guy, our phosgene, what's happened is he's gone down by the same amount that these guys have gone up. So he's gone down by 0.028 molar. Okay, so he's gone down by this many molar, and these guys have gone up by that many molar. That means at equilibrium, 0 plus that much is 0.028 molar, and then 1 take away this much is going to be 0.972 molar. So we have our concentrations of each of these at equilibrium. Just by thinking about what my initial was, what my equilibrium was, or what my change was, and kind of working it out. Remember, your ratio happens here in the change line. This is where you do your mole ratio. Not at equilibrium, it's where it changes, that is your ratio. Now we need to work out what our K value is for this reaction. So you're going to go K equals our products, which is concentration of, can't see that actually, can you? Which is concentration of carbon monoxide times concentration of chlorine divided by concentration of phosgene. This is our K, just by doing products over reactants to the power of their coefficients. All the coefficients here are 1, so therefore it's just to the power of 1. This is equal to 0.028 times 0.028 divided by 0.92972, which I put into my trusty calculator here, 0.228 squared, because obviously times itself is squared, then divided by 0.972. Gives us an answer of 8.06 times 10 to the power of -4. And now I need to work out my, my units. Looking at this, I've got molar times molar divided by molar equals molar squared over molar equals just left with molar. So therefore, my unit for this is molar for our K value. This K value is this for this certain temperature. Obviously, we haven't been given a temperature, but if you were given a temperature, let's just say that this was at, say, 25 degrees Celsius. Let's just call it 25 degrees Celsius. You would say that this is the K value for 25 degrees Celsius. Okay, K is always temperature dependent, so you need to really, probably should put a certain K and the temperature that that K was being recorded at. Hopefully that gives you a bit of understanding of how to do these questions involving this little, what's it called, table here. Initial, change, equilibrium. Your change is where you use your mole ratio. Okay, last question on equilibrium constants. This one's going to test us a bit. It's a bit harder, but let's just follow through and I'll just follow the same process that I do. First of all, we have an equation, same equation as our first question. The question is, an amount of hydrogen iodide is introduced into a 2-litre vessel. At equilibrium, the concentration of hydrogen is 0.033 molar. What amount of hydrogen iodide was first added to the vessel? Obviously I need to put added here. Okay, let's have a look at how we're going to do it. Obviously we've got a K value here. We've got an initial or an equilibrium concentration. And we say at the start, only this was added to it. So what I'm going to do is I'm going to first of all write down my equilibrium constant equation. So I'm going to, because I know it's equilibrium, it's probably a good chance that this is going to be helpful. So I'm going to go products over reactants. Okay, and now I'm also going to do my little table, because that might be helpful as well, because I've only got one here, one concentration. So I need to do my table to work out some of the other stuff over here as well. So if I just go H2, I2, HI, then I have concentration initial, concentration change, and concentration equilibrium. Now I start putting in values. I know this one here. This is my concentration of this at equilibrium. I also know that we started off with none of this to begin with. We only added this. So I'm going to go, right, blue for initial, 0, 0, and I know that at equilibrium I have 0.033 molar of that. Okay, that means I'll go black. This went up by 0.033. Okay, using my mole ratio, I can tell you that this went up by the same amount as this, so plus 0.033. So therefore, and my change here must be, given my mole ratio, twice as much as this, so therefore take away 0.66. Okay, and therefore, now in green, I know that this is 0.033, and I don't know this though, okay, because I don't know what I started off with. I need to work this out. This is a question mark. However, good thing is, over here, I've got concentration of this at equilibrium. I know my K value, and now I know my concentration of this, and I know my concentration of this. So K is 50.3 equals concentration of hydrogen iodide squared divided by 0.033 times 0.033. Okay, that means, if I get my trusty calculator here, turn it on, 0.033 squared equals concentration of HI squared divided by 1.09 times 10 to the negative 3. I can rearrange this equation and take this, multiply it over there. So I'll multiply this by 50.3, gives me 0.055 equals concentration of hydrogen iodide squared. And then I can get the square root of this. So if I just go square root of my answer, I'll get equals 0.234 molar at equilibrium. So I'll go over here in red. I'll go red now. This is 0.234. Okay, and then what I do to get back up to here, obviously this is how much was taken away to make this. So if I just add on plus 0.066, I get that my initial value was 0.3 molar, or 300 molar, however many, well, we've got 1, 2, 3, so probably 2 significant figures here, so therefore I'm going to go to 0.30 molar was introduced. It says amount, this probably might mean mole, so I might just go to number of moles equals concentration times volume. My concentration is 0.3, my volume is 2 litres, so therefore what was added in was 0.6 mole of HI. There we have it. Now, it's a difficult question if you don't know where to start. I started with writing my K value down and doing this table here. Okay, and then I tried to look at what I can use to work these out. Okay, and through writing everything down, I was able to work through this question. Without writing things down, I would have a very difficult time of working through any of these questions that I'm doing at the moment. I first of all need to write down what I know, and that's normally, when you're dealing with equilibrium, the value or the equation for K, the expression for K, and sometimes it's involving this little table here as well. Alright, that's the last one on equilibrium. I hope you've enjoyed it, and I'll see you next with acidity constants.